AI is everywhere nowadays. But here, I'd just like to speak about one particular aspect, which is how maximum likelihood estimation, which is a core technique in AI, struggles when learning interactively. So, first, how does a regular learning look, roughly? We want to build a model, like a neural network, that takes some input x and outputs a quantity to predict y. So, for instance, the network may try to predict how good is some action, like a recommendation. In such case, the input x is a description of this action of the recommendation, and the output is very likely the probability of a good event, like some reward. A simple training consists in using a dataset of pairs, x, y's, collected beforehand, in order to fit the model, which means finding the best possible value for the parameter theta of the weights of the model. And very often, this is done via maximum likelihood estimation. Okay, what is maximum likelihood estimation in general? It's a way to find out which distribution may have generated some samples. So assuming that, on one hand, we have a bunch of samples, so let's just call them z1, zn in this simple case, that are coming from some unknown distribution. And on the other hand, we have a bunch of possible distribution of candidates. And we want to find out which one of those most likely generated the samples. So often the distribution are coming from a parametric family, p of z given theta, and the objective is to find the value of theta such that p of z given theta most likely generated the data. And this is exactly the maximum likelihood estimator. And here, the probability of generated all the data points z1 to zn given theta is a product of the probability of generating each of the samples because they're assumed to be independent. And that's exactly what we do in AI. We have a bunch of pairs x, y, and we want to find p of y given x and theta that most likely generated the conditional distribution of y given x. Okay, assuming there exists a value theta star such that the samples are exactly generated from p of y given x and theta star, the big question is the maximum likelihood estimator actually getting close to theta star as we have more and more samples? So to visualize this, we're going to use a very small model. We could say a neural network with no hidden layer, which basically means a logistic regression. And this way, there are only two parameters, theta 1 and theta 2, and we can visualize what is happening in the parameter space. Okay, so let's run a simulation where we compute the maximum likelihood estimator on an increasingly large dataset. When we do this, at first, the parameter is very far from theta star. But as the number of samples n increases, it gets closer and closer. So to convince ourselves we're not just lucky with one specific trajectory, let's run 1,000 of such simulation independently. So here, each blue point is a maximum likelihood estimator on a different dataset. And we increase the size of this dataset n progressively. And we see that in all the simulation, even though they're moving in a noisy way, the maximum likelihood estimators are all getting close to theta star. They all concentrate around theta star. And it's a phenomenon completely similar to the central limit theorem. Central limit theorem describes this phenomenon for a simple average Here we're just working with a slightly more complex object, the maximum likelihood estimator, but the same phenomenon is at play. And that's basically why machine learning works at the core. Now, one thing usually makes learning a lot more complex. It's interactivity. So, we still have the real world that generate y given x according to the same distribution p of y given x and theta star. But now we don't have a dataset collected beforehand that kind of covers all the space. The dataset is built by an agent that builds a model while interacting with the world. Think of a recommender system. It chooses a recommendation X somehow, and this recommendation is shown to some user who will, maybe, watch some movie, listen to some music. And the feedback associated to this, Y, is then collected by the agent, which uses both the action he played and this feedback, in turn, to refine its model using maximum likelihood estimation. So what's a simple version of such an agent? So the agent is storing all the pairs x, y's it has generated so far, and it uses this dataset to continuously refine its maximum likelihood estimator, theta star, that gives him an internal model of the world. Okay, and this model of the world is that the probability of y given x and theta hat is sigmoid of x transpose theta hat. Now, what is the natural idea for the agent to choose the next action? Well, assuming that the agent wants to play the action that maximizes the probability of a good event, y equals 1, a reasonable strategy is to play xi that maximizes this probability under the model of the world the agent has built so far, theta hat. So here we assume that x is bounded, so it's living on the L2 ball, and this optimization is done on the L2 ball. Now the question is, when we do this, as the agent interacts with the world, it collects more and more data. So does theta hat still converges towards theta star? Let's try. Okay, it does not seem to be the case, at least in this first trajectory. So to better understand what's happening, let's again run 1,000 independent simulation and observe the parameters of each of these simulation and where they're moving towards. So again, we start with random initializations, and as the number of samples in each simulation increases, well, the bad news is that the maximum likelihood estimators do not concentrate towards the star, but they do concentrate towards something, and we see this structure appearing, the structure of a circle. And that's where I love math, because what we see appearing, we can actually describe it as a circle, and we can guess that it passes through the origin, through theta star, and we can also probably even guess that its center is exactly theta star over 2. Okay, why our maximum likelihood estimators are converging towards this circle instead of theta star? So to help the intuition, let's simplify a bit further. So instead of choosing its action in the L2 ball, so among an infinite number of actions, let's assume the agent is constrained to 2 actions only. Either it plays the first basis vector and observes an information about theta star 1, or it plays the second basis vector and observes an information about theta star 2. And let's rerun all the same simulation with that. So the maximum likelihood estimators are still not converging towards theta star, but now they're converging toward 2 segments. is a model of the word of the agent theta hat lies on the top segment that contains theta star, it's not too bad, because even though the maximum likelihood estimator theta hat did not converge to theta star, the agent is still playing the real best action, which is the second one, the one that maximizes the dot product with theta star. But if the model of the word of the agent lies on the other segment, it mistakenly believes that the first action is better, and as the agent keeps on playing the first action, theta 1 converges to theta star, but because it never plays the second action, it will forever underestimate theta star and get stuck there. So to convince ourselves that this intuition can be transferred to our general case with the circle, let's just do something intermediate and add a third action and see what's happening. So now we have 3 vectors on the ball, on the L2 ball, and if we look at the simulation, now the maximum likelihood estimators are converging towards 3 segments, and the intuition kind of stays the same that in the case of 2 actions. But maybe you start to realize that if I was to add more and more actions, all of these segments would start to approximate the blue circle we have on the right. Okay, so now we got that intuition, we can write what is this set towards which the maximum likelihood estimator converges. It is the set of possible values of theta such that if we play an action x according to theta, the true word we get, which is sigmoid of x transpose theta star, is the same as the one we would get if the real word was using theta and not theta star. So this set is sometimes called the self-coherent set. Self-coherent because when you play according to your belief, what you observe is coherent with your belief. So let's pause a bit and summarize. When the data is collected beforehand with a marginal distribution P of x that covers all the space, then the maximum likelihood estimator, theta hat, converges towards theta star. When an agent collects the data as it interacts with the word, acting according to its current estimate theta hat, and refining this estimate at every time step, then theta hat does not converge toward theta star, but towards a larger set, named the self-coherent set. So the common answer to this problem is to inject some noise in the way the agent is acting, to ensure that it plays all the action with a sufficiently large probability, and that leads to the question of how often it should play an action that is different from the estimated best, and that is called the exploitation dilemma, and there is a whole literature on this topic that is called the bandit literature. But I don't really want to explain this literature here, and I'd rather focus on showing you how understanding the geometry of the self-coherent set can lead to new ideas and algorithms, and that by giving you 2 examples. So first, let's assume that I'm giving you an information for free. I'm telling you what is the best achievable reward of the problem. You don't know theta star, but what I'm telling you is the reward that you would get if you play optimally in this word described by theta star. I'm not telling you which action leads to the best reward. I'm not giving you theta star, just what is the best reward. Doesn't seem that strong, right? But in fact, that's a constraint we can trace, because then we know that we're only looking for a value of theta that brings the same reward as theta star, that we can write r star. And that means that sigmoid of x transpose theta equals r star, where x is, well, the optimal action associated to theta. And in this case it's actually easy, because the optimal action is the one with the highest dot product with theta, and that's exactly theta divided by norm of theta, because we are on the L2 ball. So if we simplify, that means that norm of theta equals sigmoid minus 1 of r star. And this is the equation of a circle. So now we have two circles, the constraint and the self-covariant set. And they only intersect in one point, theta star. And this tells us there is no need for exploration. There is no need for injecting noise in the system. Because by integrating this constraint in the optimization problem of the maximum likelihood estimation, we get an estimator that converges to theta star. Okay, here I give you an additional information. So now let's think about a case where I don't give you any additional information. So we're back on the initial problem. And there are still ways to use the self-covariant set to imagine new algorithms. So I'm going to show you a funny idea. It's definitely not something that people have been doing in practice. It's probably not it's not optimal in any way, or not super good, but it really is about bringing new ideas from what we understand. We know that the self-covariant set is a circle fully defined by theta star. Its middle is theta star over 2, and its radius is norm of theta star over 2. We also know that 3 non-collinear points are enough to define a circle. And the origin is one of them. So we only need 2 more points on the self-covariant set, and we kind of lock the circle, which gives us theta star. So how about we alternate between 2 independent agents, meaning at each time step we're playing with one agent or the other, and these agents are maintaining independent estimates of theta star because they have independent datasets. The respective estimators will almost surely converge towards different points of the self-covariant set. And so this is theta hat 1 and theta hat 2. Along with the origin, they define a circle. And the circle in turn defines an estimator theta tilde that does converge towards theta star. So no one does this in practice. But I wanted to show you that even when the maximum likelihood estimator does not converge towards the true parameter, it is worth trying to understand the geometry of the set towards which it converges, because that can bring a lot of new ideas and algorithms.